I am excited to share our paper, Divide and Merge, published in TMLR and presented at the NeurIPS workshop. This work addresses a critical issue in end-to-end autonomous driving models, perception negative transfer. Specifically, while end-to-end training improves prediction and planning, it actually hurts the performance of fundamental tasks like object detection and tracking. Let's take UniAD as an example. It uses a two-stage training process. Stage 1 trains only the perception modules, while Stage 2 trains all modules end-to-end. When we normalize the perception performance to Stage 1, we observe a significant degradation during the second stage. This degradation leads to collisions. Here are two examples from closed-loop planning evaluation. In the top scenario, the ego vehicle faces an oncoming safety-critical object. The model gets confused by the object's orientation and fails to react. In the bottom example, poor detection of the side vehicle and the construction vehicle leads to a crash. We argue that this negative transfer is caused by a conflict between motion and semantic representations. Existing methods force a single feature vector to represent an object. In the second stage, this feature vector must learn two different types of information. Consequently, it has to sacrifice semantic features learned earlier, causing the drop in perception performance. We propose to divide the learning of semantics and motion, parallelizing perception with trajectory prediction. But prediction depends on perception. How can the model predict without seeing first? To solve this, we designed a recursive decoding process, mimicking a recursive Bayes filter that exchanges reference points between the two tasks without gradient flow. This successfully divides the learning process, mitigating negative transfer. Additionally, we noticed that the correlation between similar tasks was underutilized. Since object detection and online mapping are both semantic tasks, we propose to merge them to promote positive transfer. Applying this architecture to UniAD, which we call DMAD, we see that our perception already outperforms the baseline in the first stage. Crucially, this high performance is maintained during the second stage, effectively eliminating the negative transfer. Most importantly, this improved perception translates directly to safety. Here are the collision rates for UniAD in open-loop and closed-loop evaluations. Applying our divide and merge strategy reduces collision rates by a large margin. Let's revisit the failure cases. On the right is our method, DMAD. Here, DMAD successfully detects and predicts the oncoming object, safely avoiding the collision. In the second scenario, DMAD demonstrates robust detection of both the side vehicle and the construction vehicle, resulting in smoother planning and no collision. But we didn't stop there. Our paper also validates this success on sparse drive and uses SHAP value analysis and attention visualizations to verify our design. That was just a glimpse. To see the full insights, scan the QR codes for our paper and code. Thank you for watching.